Next we'll come to heat. Heat. Heat is denoted by the small letter Q. We can say that heat. So what is heat actually? It's nothing but a form of energy. It's a mode of energy, we can say that, which is exchanged between the system and the surroundings. Got it? As a result of difference of temperature between them. Alright, what I said you, heat is nothing but a form of energy which is exchanged between the system and the surroundings. How it is exchanged? As a result of difference of temperature between them. Difference of temperature between system and the surrounding. The heat is exchanged. Either it can be evolved or it can be absorbed. If the heat is absorbed, then Q value is positive. If it is evolved, then the Q value is negative. Remember, for exothermic process, Q value is negative, and for endothermic process, the Q value is positive. Remember it. Now, next is we have to convert sometimes the calories into joules. So 1 calorie is 4.184 joules. We can say that 4.184 joules. Remember it. You have read in the lower classes that is 4.2 joules, but exactly the value is 4.184 joules. We can say that. Clear? And we can convert into joules into calories also if you like. So what you can say, calorie is this many joules. So 1 joule will be 0.239 calories. We can say that. Alright, 1 joule is equal to 0.239 calories, we can say. So next is work and heat, both are, I've said you, they are the path function. They are not the state function. I have explained you also. Now let me take here one more example and explain it. Let me take one more example. Let me take a graph and explain you. I think you will be following it, this particular graph. P, V, same thing, P, V, same thing, P against V. Fine. Now a person wants to, what you can say, he wants to go from here to here, from A to B, if a person wants to go. Alright, so what he can do is that he can go directly in this way, A to B. Alright, see the path. Here I am saying heat is a path function. That is what I am explaining here. That heat is a path function. A person is here at A, he wants to go to B. He can go directly from A to B in this way. Fine. Now, next graph you see. Saying the person is at A and B. What he can do is that he can come down here and he can go in this way also. This is also possible. This also is possible that he can come down here and he can go in this way. He can come down here and he can go in this way. It is possible. Why not? Now, next is a person is at A, he wants to go to B. So, this is A and this is B. So, what he can do? He can go in this way and he can go in this way. That also is quite possible. Clear? If he wants to go from A to B, then what he can do? He can go in this way and he can come in this way. If he wants from A to B, he wants to go, he can come in this way and go in this way. If he wants to go from A to B, he can go in this way. So there are 3 different ways. So it's what? It's a state function or it's a path function. What I have told you here, the path, the 3 different paths I have shown you. The 3 different paths. The destination is the same, starting point is the same. Starting point is A, this ending point is B. It is same. It is same here. But there are 3 different paths I have shown you here. Due to which it proves what? That heat is a path function. Got it? So hence, heat is always a path function. It's not a state function. Fine. I hope you understood this particular thing. So here I have shown you the work done. That's P into V will give you what? Pressure into volume is what? Work done. So that is the same as heat, because work done is also measured in joules. Heat is also measured in joules, so to say. Fine. Now, next is we'll come to the first law of thermodynamics. First law of thermodynamics. The first law of thermodynamics. So what is the first law? Energy can neither be created nor be destroyed, or it can only be converted from one form to another form. This is in accordance with the law of conservation of mass or the law of conservation of energy. We can say that. The first law is in accordance with the law of conservation of energy or law of conservation of mass. Law of conservation of mass also is the same thing. That is, mass cannot be created. The total mass before the reaction is equal to the total mass at the end of the reaction, we can say that. So, or in other words, the mass of the reactant is equal to the mass of the product, which you have already studied. Now, the first law is in accordance with this particular law of conservation of energy. Alright, which states that energy can neither be created nor be destroyed, although it can be converted from one form to another form. It can be converted. For example, in your home, when you're switching on the bulb, the switch, the electricity flows into the bulb, and as a result, the bulb glows. The electricity flows into the fan, as a result, the fan moves. So when the bulb glows, electric energy is converted into light energy. Energy remains constant. When the fan, it rotates, what you find is that electrical energy is converted into mechanical energy. Energy remains constant. So it can be converted from one form to another form. We can say that. Clear? Fine. Or you can say that the total energy of the universe, universe means system and surroundings, alright, remains constant. Alright, we can say this way also, the first law. The total energy of the universe consists of the system and the surroundings. It remains constant, although it may undergo transformation from one form to other. Although there may be a transformation, there may be a change. Transformation means change from one form to another change. But the total energy of the universe means, I said you, it is not the sun, moon, earth, Jupiter. No, I am not talking of the planetary system. Alright, here in the universe means I am talking of the chemistry lab, alright, which consists of the system and the surroundings. I have already mentioned in my first AV about it. In the beginning of this chapter, I have mentioned it. So, now here, energy of an isolated system is always constant. Isolated system means neither energy is lost nor it is gained. For example, when hot tea is kept in a thermos flask, hot tea, so it remains hot only, because neither it gains energy from the surroundings nor it loses its energy. We can say because it is isolated. Thermos flask comes under isolated system. We can say that. Clear? So in this way, the energy of an isolated system is constant. So either of this definitions, we can say that. Either of these definitions. Got it? Now, that is from the first law also we come to know that it is impossible to construct a perpetual motion machine. From the first law we come to know, by reading the first law we come to know that we cannot construct a machine, perpetual motion machine. What does it mean? It means a machine which runs by itself without consuming any energy. Have you seen any such machine that will run by itself and will not consume any energy? Alright, have you seen any vehicle that is not consuming petrol or diesel or any other energy and it is running by itself? Is it possible? Up to now it is not possible. Alright, no, it's not possible. So hence, it is impossible to construct a perpetual motion machine because the first law is saying the total energy remains constant. Isn't it? So we cannot construct a machine which runs by itself without consuming any energy. No, not possible. Alright, clear. So this statement was given by Helmholtz. We can say that. Helmholtz gave this particular statement by looking at the definition, by studying about the first law, we can say that. Alright, so from the first law itself we come to know there is an exact equivalence between heat and the work. There is some relationship, already we have seen it. There is some relationship, there is some exact equivalence between the heat and work. For every 4.184 joules of work done, 1 calorie of heat is produced. For every 4.184 joules of work done, 1 calorie of heat is produced. Just now I said 1 calorie is equal to 4.184 joules. So you can say that. Clear? Or vice versa. It may be released also. Either it may be produced endothermic or it can be exothermic also. It may be released also. We can say that. So hence we come to know from this, we conclude this particular one from the first law of thermodynamics. Now next is what is the justification of this particular law? How can we justify the law? The statement, of course, we have said that energy remains constant. For an isolated system, but you can say that there is the total energy remains constant. Energy can be converted from one form to another form. Energy remains constant. We cannot construct a perpetual motion machine. So many things I said. These are all the theoretical justification. Practically, what is the justification of this law? What is the justification? Just now I was saying you also the example. That is a practical justification. How much energy you are supplying, that much energy you are getting it. Alright, less than that energy you are getting it, because some energy is always wasted. That is for that reason it said, we cannot construct a perpetual motion machine. We cannot construct a machine which runs by itself without consuming energy. Some energy is always consumed. How can we say it is consumed? When you are switching on the light. Alright, when you are switching on the fan, what happens? The electricity flows through the wire to the light, and the bulb glows. We can say that. Do you think there is no energy is wasted here? So of course some energy is wasted here. So it is being converted from one form to another form, we can say that. Alright, now, okay, fine. Now these all things I've read in lower classes also about it. It's not a new thing. But here I'll give you something new, alright, to make you understand that total energy remains constant. To justify the first law, we can say that. Alright, now it's a very simple example I'm giving you, so to say. Now suppose when water decomposes, it decomposes to give you what? Hydrogen and oxygen, H2 plus half O2, let us say. When water decomposes, how water will decompose? When you will pass electric current, when you will go for electrolysis of water, then only the water will decompose into hydrogen and oxygen. You know that hydrogen will be collected at cathode, oxygen will be collected at anode. Now when you calculate the heat, you will see 285.8 kilojoules of heat is required per mole of water to decompose 1 mole of water. There is 285.8 kilojoules of heat is required to decompose 1 mole of water. This is being calculated. This is being calculated, mind it. It is required. Similarly, when hydrogen combines with oxygen to form a molecule of water, as you can see it here, then it liberates same amount of heat, 285.8 kilojoules of heat, 1 mole of water it liberates. It has been seen practically and it has been checked, we can say that. Clear? When water decomposes, when 1 mole of water decomposes to form this, it requires this much amount of energy. 1 mole, mind it, per mole. Now, when hydrogen and oxygen they combine to form water, this much amount of energy is released. So it is verified. It is verified that total energy remains constant, we can say that. Only it can be converted from one form to another form. Understood the justification? Now we'll come to the mathematical formula. Alright, for the first law of thermodynamics, we'll come to the formula, mathematical formula. We'll derive a formula from the first law of thermodynamics. It's very, very important. Now listen here. Suppose, let us say the initial internal energy of a system is there, is U1. Initial internal energy of a system. Initial, mind it. Alright, you may write it down here. This is initial internal energy of a system. I've said you, I'll take the internal energy as U, capital U. You may take it as E also, no problem, but I'll take it as U. Clear? Yes. Now, initial internal energy is U1. Let us say it absorbs some amount of heat, that is Q. As a result, the internal energy rises to, what is that? It will be U1 plus Q. It absorbs, listen to my every word, absorbs Q amount of heat. Absorbs means it is plus, positive. Alright. So hence, the internal energy is now U1 plus Q. It absorbs Q amount of heat. So the internal energy is U1 plus Q. Now if further work is done on the system, that is W, then the internal energy will further increase to, that is nothing but Q plus W. We can say that U1 plus Q plus W. Understood what I said? If further work W is done upon the system, upon, not by the system. If further work is done upon the system, then the total internal energy, work done upon the system. So when the work is done upon the system, the work done is positive. So the internal energy will be now U1 plus Q plus W. So if I make a particular sentence, I can say in this way. Let us say the initial internal energy of the system is U1. It absorbs Q amount of heat and the work done upon the system as a result is, got it, W. Due to which the total internal energy or the final internal energy of the system U2 is nothing but U1 plus Q plus W. Alright, when initial energy is this much, it is absorbing this much amount of heat, then the work is done upon the system is this. As a result, the final internal energy is nothing but U2. So final internal energy of the system is U2, which is nothing but U1 plus Q plus W. Now see, U2 minus U1 is equal to Q plus W. What is U2 minus U1? Delta U. So we got the formula del U is equal to Q plus W. This is the mathematical relation of the first law of thermodynamic. We can say that. Now if Q is equal to, what you can say, W is equal to P del V. W is equal to. Then what we can say, delta U is equal to Q minus P del V, because generally the W is taken to be as negative by convention. By convention, we consider W as negative. Alright, by convention, if it is said to be as, it is negative. Otherwise, if it is the work of compression is given, if it is the work of compression, you know, it is nothing but, or the work done by the system is given. If instead of that is upon the system, it is by the system, then this W will be positive. We can say that the work done will be positive. So instead of minus P del V, I can write it as nothing but Q plus W. Okay, fine. So in this way, that it depends upon the question, we can say that. Now next is what you find is that what I was saying, that it is an isothermal process. Alright, in an isothermal process, the internal energy is 0. I've said you delta U value is 0. So that is in case of isothermal process, the formula will be 0 is equal to Q plus W. So Q is equal to minus W. Alright, again I repeat, in case of isothermal process, isothermal, I've told you earlier also internal energy, del U will be 0 in case of internal isothermal. See, temperature remains constant. Why the internal energy is going to change if the temperature remains constant? Because internal energy depends upon temperature. So hence del U will be 0. So when del U will be 0 in case of isothermal process, where you will use this, again I am saying you repeatedly, it will be used in numericals. So hence listen to my word, very important. It's very important. Listen to my word very carefully. So del U will be 0 in case of isothermal process. So when this will be 0, so what will I write? 0 is equal to Q plus W. So Q is equal to minus W, or W is equal to minus Q. So this is the expression you get it in an isothermal process, so to say. We can say that. Clear now? So this is the mathematical relation for the first law of thermodynamics. We got it. Now next we'll come to, that is enthalpy. Another state function. Enthalpy. Enthalpy is what? Enthalpy is nothing but the work done, heat calculated under constant pressure. We can say that. Heat calculated under constant pressure is called as enthalpy. Alright? In terms of saying heat, I can say that heat calculated under constant volume is known as internal energy. Alright? What is enthalpy? Enthalpy is nothing but heat. In simple words, in lower classes you have studied enthalpy. There your teacher has said you that enthalpy means heat. But here I am taking little bit more deeper. I am taking little bit more deeper. So I am making your knowledge much more wider. So what is the difference between the heat and enthalpy? Enthalpy means heat calculated under constant pressure. That means enthalpy is another letter, we can say H. H is equal to QP. We can say that. Clear? H stands for here enthalpy, and H is equal to QP, heat calculated under constant pressure. In the same note, under the same conditions, we can say U is equal to QV. That is internal energy is nothing but heat calculated at constant volume. When the heat is calculated at constant volume, that is nothing but known as internal energy. So delta U is equal to QV and delta H is equal to known as QP. Where from I got delta H? On first only I said you that enthalpy is a state function. It is not a path function. It is a state function. Alright, clear? Just like internal energy, enthalpy is also a state function. We can say that. So hence, that is from the first law we got it. That is what we got it in the first law. Del U is equal to Q plus W. Del U is equal to Q plus W. So here, what you can write? Del U, I can write it as QV. Now this, if it is at constant pressure, if this heat is calculated at constant pressure, so I can write it as QP plus W, and W also I can write it as P del V. I can write it as P del V. If the work is done, what is that? By the system. And if the work is done by the system is what? The work done upon the system is, what is that? The work done upon the system, that is nothing but positive, and the work done by the system is negative. Clear? We have already studied this particular one. Don't get confused. The work done by the system, we have already studied. That is work done. If W is taken to be the positive, it is the work done. What is that? Upon the system. We can say that. That is the work done by compression. Upon compression. Alright. And W is taken to be as negative if the work is done by the system. That is expansion. By the system it is. Alright. So in this way, we can say this particular thing. I can write it down here. I hope you understood. Delta U is QB. And if this Q stands for the heat calculated under constant pressure, if this heat stands for, if this Q stands for, then instead of that Q, I can write it as QP. This is QB, then QP. And the same note I am writing now, just to compare it. Understood? Clear? Say, and this we got it as P delta V. We can say that. Clear? I can write this particular thing. Now, you may ask that how did I arrive to this particular conclusion? Okay, we will do one thing. We will derive it. This formula, that is, we'll derive it and we will see it. Clear? So, we'll derive this particular formula. So, now, that is in the next step we will see. Thank you.